Hello everyone, my name is Finding Pepper, and welcome to How to Code Perlin Noise Terrain Generation in Scratch. If you don't know, Perlin Noise is an algorithm to generate realistic looking terrain. I'll go over the specifics of how it works in a moment. In this video, part 1, I'll just be coding up the algorithm as well as a top-down viewer of it. However, in part 2, I will cover how to display the terrain we've generated in 3 dimensions, so you can look and move around it. Alright, so before we begin coding, let's go over how this algorithm works. So this is what the terrain that it generates looks like. Now this algorithm has 2 steps. Step 1 is creating a grid of random vectors. As you can see here, we have an in-by-in grid, and at each of the lattice points of the grid is a vector in a random direction. To find the height of any given point, we use information about the 4 vectors on the corners of that point's grid cell. Alright, let's talk about generating these gradient vectors. So we know they must be generated in a grid. Their direction should be random, otherwise our noise might be too predictable. And all of these vectors should have the same magnitude or length. This last part is a little bit more complicated than it sounds, because vectors are defined not by their angle and direction, but by the difference in x and y positions between their start point and end point. So we need a way of taking a direction and a length and turning it into x and y coordinates. To do that, we can use the unit circle. So for each vector, we choose a random direction, or angle if you will, and then find the point on the unit circle in that direction. The coordinates of that point are simply an x of cosine of the angle and a y of sine of the angle. If you haven't learned sine and cosine yet, that's totally fine, because this is essentially the definition of sine and cosine. Alright, let's look back at our vectors again. You may notice that I've called them gradient vectors a few times. That's because at each vector, we generate a gradient, as shown here. The darker gray parts are negative in value, and the lighter gray parts are positive in value. The point of the gradient at the start of each vector is 0 in value. As we move from that point in the direction of the gradient, the value of each point increases, and as we move in the opposite direction of the gradient vector, the value of the point decreases. Now you can see this in action when we draw grid lines over our terrain. You'll notice that at each of the lattice points of the grid, where the grid lines meet, is a border between land and water. That's because I'm defining the water as anything with a height less than 0, and the land as anything with a height greater than 0. So the lattice points of the grid then have a height of 0, which makes sense when we remember our gradients, because at the start points of each of the vectors, the value in the gradient is 0. Now to find the value of any point on this grid, and I mean any point, not just points where vectors start, we need to take some blend of the vectors surrounding it. To do that, we can use the fade function. There are several different fade functions, but the one we're using involves 5th, 4th, and 3rd powers. Shown here is a graph of that function. We can imagine the x-axis as the distance from the start of a gradient vector, and the y-axis as the impact that gradient has on the height of the point. But wait, that's not right. That would mean that a higher distance would mean that the gradient has a higher impact, which just doesn't make sense. To fix this, we simply need to flip the graph. I'll get into the details of that more later, but for now, it's time to move on to step 2. So step 2 is finding the height of any given point based on its x and y position within the cell and the gradients surrounding it. So let's start by defining some basic values. Let I and j be the x and y of the cell which the point is in. We can find that by using the floor of x and the floor of y. So we're saying that each cell has a width and height of 1. Then we'll let u and v be the x and y of the point within the cell. So if the point was at the bottom left of the cell, u and v would both be 0. If it was at the top right, u and v would both be 1, and if it was somewhere in the middle, u and v would be somewhere between 0 and 1. Okay, now that we've got that, we can define our red gradients. We'll name each of them based on their position. The bottom left will be G00, the top right will be G11. Remember that these gradients aren't anything fancy, they're just groups of 2 numbers, a change in x and a change in y, from the start to the end. Keep that in mind as we keep going. Alright, so we've defined our 4 gradients. Now you may notice on the picture we also have green vectors. Those can be defined easily in terms of u and v. For example, the green vector running from the bottom left point of the cell to our point is simply two numbers, u and v. So keep that in mind in our next step. In our next step, we perform an operation called the dot product on our red vector at the bottom left and our green vector at the bottom left. Now the dot product is a method of combining two vectors into a single number. The way we compute the dot product is by multiplying the first term in one vector by the first term in the other vector, and then we do that for each of the terms, multiply the second term in one by the second term in the other, and then once we've done that, we add them all together. Remember that our g variables hold two numbers, an x change and a y change. Now you may be wondering what the dot product is exactly. To understand the dot product more, let's take a look at this diagram. We have two vectors here and we want to compute the dot product between them. We can use our formula, x component of vector A times the x component of vector B plus the y component of vector A times the y component of vector B. But what exactly is this doing? The result of the dot product is based entirely on the magnitude of the vectors and the angle between them. So if we rotate both vectors the same amount, nothing should change. Let's try that. Rotating it so that vector B has no y component, like so. The dot product should be exactly the same here. However, we've just simplified the equation, because the y component of vector B is 0. So this equation simplifies to the x component of vector A times the x component of vector B. That's right, the y component of vector A drops out entirely. So from this, we can see that the dot product is sort of like taking a vector A and multiplying it by vector B. However, only taking into account the part of vector A that is moving in the same direction as vector B. Now, there's nothing special about vector B. We could have just as easily rotated it so that vector A was the one with no y component. You can see if these lines are perpendicular instead, meaning they meet at a right angle, the dot product becomes 0. They are pointing in entirely different axes. If vector A is moving in the opposite direction of vector B, the dot product will be negative. And if it's moving in the same direction as vector B, the dot product will be positive. Now let's try, rather than just computing the dot product for 1 or 2 points, computing it for a whole bunch of points. We'll move the start point of vector A to each of those different points, and at each of those points, we'll record a brightness value representing the dot product. A higher brightness will represent a higher dot product. Let's see what happens when we try that. And oh ho, it is a gradient! Wow, this is what we're doing with the dot product. We're creating a gradient of values centered around the start point of each of the vectors. If we rotated the vector, the gradient would rotate too. So there you have it, that's what the dot product is being used for. This next image takes our fade function into account as well. So this is what our terrain would look like if we only had one vector. The lighter gray part represents a hill, and the darker gray part represents a lake or valley. Alright, hopefully you understand the dot product a little bit better now, so let's head back to our Perlin noise formulas. Okay, so we've got the dot product of the two vectors at the bottom left point. The next steps is to compute those dot products at the other 3 points. Again, we'll compute the dot product between the red vectors and the green vectors at those points. To find the green vectors at those points is slightly more complicated. However, we can do it pretty easily by just subtracting 1 from u or v respectively. You can see that 1 minus u is the distance between the point and the right side of the cell. However, we want a negative direction, so we can just reverse that and say u minus 1 to indicate that the vector is moving to the left and not to the right. And you can see in our equations that we use that fact. So now we've got numbers representing the difference between the red and green vectors at each of our 4 corners. I'm labeling them just like we label the gradients, and followed by 2 numbers representing the coordinates of the point at which the vectors start. Now we've got the corners, we can begin to work inwards to try to find the value of the point itself rather than just the corners. To find the number of the point itself, we'll need to have some combination of these 4 values, which I'm labeling in purple. To note what mix exactly, we'll need to use our fade function. So we need to compute the fade of u and the fade of v. Remember from our fade function graph, a higher distance results in a higher impact. So what we want to happen is when our point is farther to the left, say, the gradients on the left will have a higher impact, and when the point is farther to the right, the gradients on the right will have a higher impact. We can tell how far to the right or left it is by the value of u. The higher the value of u, the farther to the right our point is. When u is bigger, the fade of u is also bigger. So we want to multiply the dot products of our gradients on the right by the fade of u, so that when the point is farther to the right, those gradients have more of an effect. The gradients on the left will multiply by 1 minus the fade of u, so that when u is lower and the point is farther to the left, those gradients will have a higher impact. So let's see that in equations. The left dot products, those are the ones that have a 0 as their first number, we multiply by 1 minus the fade of u. And the right gradients, the ones that have a 1 as their first number, we multiply by just plain fade of u. Now you'll notice we haven't mentioned v at all. Now we're starting by just getting the fade between the right and left numbers. So these points can be thought of as the values on the bottom and top of the cell, but at the correct x position. So once we've found those, we need to blend those together to get the final value of the point at the correct x position and the correct y position. We can do a similar thing that we did with the fade of u, but with the fade of v instead, because v is how far up or down the point is in the cell. And this will finally give us the value of our desired point. Now, I understand if you didn't understand all of this, but if you want to understand and you're still scratching your head, either watch this section over again or go down into the comments and ask a question, because I'll be happy to answer any questions you have. Do not hesitate to ask. On the other hand, congratulations if you did understand all of this. Now that we have our equations, it's time to actually code them. Alright, so create a new blank project, and then we'll start off with step 1, generating our gradients. So make a block called make gradients. Run without screen refresh. Now we need a way to store our gradients, so make 2 new lists, one called gradient x, and then I'm going to make all variables and lists here for this sprite only. So every variable and list you make should be for this sprite only, though if it's not the end of the world. It doesn't actually matter because we're only using one sprite. Now I'm going to make another list called gradient y, and these will hold the x and y directions of our gradients. Now they're held in a grid, so we're going to use the first item in the list as the bottom left of the grid. Then as the index increases, we move to the right in the grid. But once we get beyond the width of the grid, we loop back around to the next row. Speaking of which, we need a variable to hold the size of our grid, which I'll call grid size. Now I'll get a simple when flag clicked. We can set grid size, and then I'm going to choose the number 7, which might seem like an odd choice, but it will make more sense later when we display the world. But you can of course set this to whatever you want. I'd recommend not setting it to too big of a number. Now in our make gradients blocks, we'll start off by deleting all of gradient x and gradient y. Then we can simply repeat grid size squared, or grid size times grid size, to get all of our gradients. Then we need to come up with a random direction for our gradient. So I'll make a variable called dir, and set dir to a random direction, that is 0 to 360. Then we can add the cosine of dir to gradient x, and the sine of dir to gradient y, just like we talked about with our unit circle. Alright, I'll use this block when the flag is clicked. Let's run this and show our gradient lists. We should see they each have 49 items in them of a variety of different values. Now for step 2, which is finding the height at a given point. I'll make variables x and y to hold what that point is. Then we can make our block called find point height. Run without screen refresh. We're going to start off by finding those I, j, u, and v values. I'll give them slightly more descriptive names so we can remember them better in the future if we need to. I'll call base x and base y will be our names for the coordinates of the bottom left of the cell which it's in. We'll set these to floor of x and floor of y respectively. Then I'll call the u and v values cell x and cell y. because they represent the x and y coordinates within the cell. So set cell x to x minus base x, and cell y to y minus base y. Alright, and now we need to find our gradients. This will be a little bit more tricky. I'll make variables to hold these, and because we can't store vectors in a single variable in Scratch, we'll need to make separate variables for the x and y components of each vector. Call these g00 and then x, g00y, g10x, and g10y, g01x, g01y, g11x, and g11y. To find the index of a position x, y in a grid, we need to use the following formula. Our formula is y times grid size plus x. And then we need to add 1 to this because lists in Scratch start at 1, not 0. So this makes sense because when we change x by 1, we move 1 grid cell to the right. Then when we change by y, we need to loop all the way around to the right and then back up to above where we were. So when we change y, we need to add grid size to our index of the list. So when we set our gradient variables, we'll use this formula. So start by setting g00x, that's our first one, to item, and then we'll duplicate this formula, and for our y, we'll use our base y. For the x, we'll use base x. And then same for g00y, except we're looking in the gradient y list this time. Now for our g10x, this gradient vector is 1 to the right of our gradient at 0, 0. This one's at 1, 0. So we need to add 1 to the base x. Now we have a plus 1, which is the same as a plus 2. Now we do the same for the y again, g10y, and change the list to gradient y. Make sure you're choosing the correct variables here, because if you get the wrong variables, that could cause issues and you might have trouble finding them. Okay, now for our g01, we need to add 1 to our base y, like so. And the base x is just plain plus 1. And then do the same for the gradient y and g01y. Then, finally, our gradient at 1, 1. We're adding 1 to the base y, and then 1 extra to the base x. And then again for the y. Alright, so all of our gradient getting formulas are right here. Our next step is getting the dot products of the gradients at the 4 corners. Remember, those are our dot products between these g gradients and then the gradients to the x and y position within the cell, which use the cell x and cell y variables. We need new variables for these. I'll call them in 0, 0, in 1, 0, in 0, 1, and in 1, 1. Just like we did in the explanation. Start with in 0, 0, then we'll use our dot product formula, adding the sums of the x's, that is g00x times cell x, and the y's, which is g00y times cell y. Then for our other 4 corners, start with the in 1, 0, replace our g00 with g10, so g10x and g10y. Then for the cell x, we're going to subtract 1 from it, because this gradient is coming from the right rather than the left. Remember, we talked about this in the explanation. Then for in 0, 1, again use the corresponding g variables, g01x and g01y. This time we're subtracting 1 from the cell y, because this is at the top left. Then finally, and 1, 1, with g11x, g11y, and both of our cell x and cell y will be minus 1. Alright, so we've got our dot products. Our next step is applying the fade function to our cell x and cell y. So make variables, fade of cell x and fade of cell y. We'll start with the x, set fade of cell x, and then we might recall that we need powers. Our first one is 6 times cell x to the 5th power, But we have no power block in Scratch, so we just need to have 5 cell x all multiplied together like this. So 6 times cell x to the 5th minus 15 times cell x to the 4th, then plus, and then the plus is going to be around this whole thing, plus 10 times cell x cubed. Then we stick this in here, then we get the fade of the cell y also. And here we just need to replace all cell x's with cell y's. I'm just going to start by removing all of the cell x's first so we don't accidentally forget any. Then we can duplicate all of our cell y's. So just replace all the cell x's with cell y's for this equation. Alright, now that we've got these, we can find our in x0 and in x1. Remember, these are the numbers representing the points at the bottom and top of the cell, but at the correct x position. Set in x0. Then for this one, we need to get the correct blend between in 0, 0 and in 1, 0. So with a plus, we add in 0, 0 times 1 minus fade of cell x plus in 1, 0 times plain old fade of cell x. Then for in x1, we simply replace our ins with the ones that have the second number of 1. So in 0, 1 for our first one, and in 1, 1 for our second. Once we've got this, we can find the value of our final point. We need to make a variable for this, and I'll call that height. We set height to in x0, and then in x0 times 1 minus fade of cell y plus in x1 times fade of cell y. Wow, that is a lot, but we have got it. We have our height of our point. Now all that's left to do is draw our world. So I'll make a block called draw world. Essentially what we'll do is start on the bottom left of the screen, move along the screen, doing each row one at a time, and at each point finding the height and then drawing a color pixel there based on that height. We're going to use the pen for this, so add the pen extension. At the top we erase all and set pen size to 1. Head to the bottom of the screen by setting y to -180. Then we'll repeat by the screen's height, which is 360. Each time we will draw a row. To draw a row, we start by setting x to the left of the screen, -240, and then repeat 480. Each iteration, we will move one to the right by changing x by 1, and then in the y loop, the outer loop, we'll change y by 1 each time. However, it's not our x and y positions that determine what point we get our height at, it's the x and y variables. So we'll also need to set y to 0 at the start of the loop, and then set x to 0 at the start of the inner loop for each row. Then inside our inner loop, we change x. Then how much do we change by? Well, we change by grid size over 480. So that total, after 480 iterations, we'll have changed x by grid size. However, there's one slight problem. By grid size, we do not mean the number of grid cells, we mean the number of grid lines. And this is 1 more than the number of cells, so we actually need to subtract 1 from the grid size. That's why I set grid size to 7, so that it's a nice even 6 cells. So that while the grid size is 7, the number of cells in each row is actually only 6. Alright, and we can also change y in our outer y loop. And we change this by exactly the same amount, so we have a square grid. We won't actually be able to display the whole grid, it will go above our screen. Alright, now for each of these x positions, we use our find point height block. Then I'll set pen color to a white color, or some sort of gray color. And then we can change the pen brightness based on the height. So change pen brightness. Well, first we need to add 1 to our returned height value so that this never becomes negative, because maybe I forgot to mention this, but the resulting height value from our find point height block will always be between -1 and 1. So we add 1 to it, so it'll be between 0 and 2, and then we can multiply by 50, so it gets between 0 and 100. then we can pen down, pen up to draw a single pixel. Okay, now we use this block when our flag is clicked. Let's run this. Oh, and oops, I used to change pen brightness block. We should be setting pen brightness. Let's run this, and there is our world. Now I'm going to disable run without screen refresh in this so it looks a little smoother. Now it's generating much slower, but if we shift click the green flag, we'll enter turbo mode, and this is generating much faster now. And there we can see our noise patterns. So the lighter gray is sort of hills, and then the darker gray is sort of where the water would be. So you can sort of see the patterns of where the waterways would go here. Now you'll know if you did something wrong because the noise will be choppy. There'll be harsh lines and things. If you did something wrong, you'll just need to go back to your find point height block and check over these formulas. Okay, but we can do better than this. We can actually draw our water and our land. So around our setting color, we can check if height is greater than 0. In which case, we can set pen color to green for land, something like this. And I'll make the saturation full, but of course you can change that. And then, yeah, we can use the same formula here in fact. Otherwise, if height is less than 0, we can set pen color to blue. And then I'm actually going to add 2 here, so the range of numbers is between 50 and 100, because remember, our height is always going to be 0 or less here. Okay, let's run this. And now we have our world. Awesome, this is looking great. And now you can clearly see where the land and water is. This green color looks a little bit different than the one I used in my example, but that's totally fine. You can fiddle with the colors if you feel like it. You might have noticed I also had sand in my example. To add that, we can just get an if-else and when height is greater than 0, check if height is less than like 0.05 or something, then set color to as yellowy color. Then we don't even need to worry about brightness here. We can just have that same constant yellowy color. There is our sand. I'm going to make this slightly darker. Okay, awesome. There we go. Our very own terrain generator using quite advanced algorithms. Now this is still pretty simple as things go. There are some more improvements we could do to make this even better, but I may have to save that for a later video because this is the end of the video. In the next part, we will be working on displaying this terrain in 3 dimensions, so we can move and look around it. With all that said, I hope you enjoyed this tutorial. Have a great rest of your day, and goodbye!